So here's another interesting thing. When you put things in pipes, what happens? And when you want things to move in a pipe, what you will realize is pipes actually have two surfaces, three surfaces, all around. So remember when we drew this, we said that the one closest to the surface was almost at rest. So now that you have multiple surfaces, what do you think the other side would look like? That is experimentally known. Friction to the outside will be slower than the one in the middle. So the centermost layer will be the fastest. And a lot of work was done by the same guy, the Poiseuille, Poiseuill.
You can spell it.
So his law, and he worked a lot on this, and this was all done experimentally. And what he found was, because he wanted to figure out how to make fluids flow in, say, IV tubes. How do you give IV to somebody? How thick a fluid is depends on how much I can give somebody and things like that. He was working a lot on this. And so he developed experimentally this formula that says the volume of what I want to transfer is directly proportional to r to the power 4th of my tube. The rate of flow he found experimentally was proportional to the 4th power of r. Can you imagine how much work goes behind that? How many different sizes he had to use, and lengths and radiuses and all the things that came into play? And do you know what this proportionality constant is when you change it? Nope. He actually found this was pi delta p divided by 8 eta L.
Wow.
Yep.
How does he find that?
Experimentally.
Yeah.
Where eta is the viscosity, L is the length, P is the pressure, R is the radius of the tube he's using, delta V over delta T is the rate at which he wants to supply the fluid. Right? Where L is what, guys? Length of the tube. Eta is viscosity. R is the radius of the tube. V is volume of fluid. Time is time. Delta P is pressure. Oh, actually, I should define that. Delta P is the pressure difference over L. The length. So if it was going from, this height to this height, or whether it's going from this height to this height, or this height to this height. Remember when anyone got an IV in them at some point? Mm-hmm. Where do they just put it next to you?
I cried. I got blood drawn.
That difference is delta P.
What if it's totally horizontal?
Yeah, it won't flow.
So it has to be like propped up kind of.
It has to be from, it's like a water tower example. It has to be higher to reach you. Because you're pushing it in, right? And the pressure is what's pushing the thing into your vein. So if you put it down, nothing will flow. It'll just be like water. What happens to water?
Yeah, it just sits there.
It just sits there. There is another formula that you guys should know, which is I can also rewrite this as dm over dt, but in that case, an additional thing gets added here. Anyone want to hazard a guess on how that happened? What is volume?
Fast times that's
Yeah? So if I have a D and a D, may I replace that?
sure.
This is an important term. You'll see it in lots of times. So it's called mass flux. And there is another long derivation, which luckily for us, we won't do it in this class
Yeah.
for once. We should probably know what the center VC is. Remember, this is not critical velocity. This is velocity at the center. And it can be derived at the center. So I don't know, if somebody asks you to calculate that, you should probably know how to do this.